We're starting section 4.5 today, which is on integration by substitution. Integration by substitution. The first time we work through this process, it is going to seem completely foreign. You'll get the hang of it. I'm certain of that. So example 1 says the integral of cosine of 4x minus 1 dx. Notice if we needed to take the derivative of that, which it doesn't ask us to do, but if we were asked to take the derivative of cosine of 4x minus 1, we would have to use the chain rule. We do not have a chain rule for integrals. We don't have a product rule. We don't have a quotient rule. For products, quotients, or composite functions, which is when we use the chain rule. For all of those, we'll use this process, integration by substitution. And this is how it looks. This is how it works. We define a new variable, usually it's u, to be 4x minus 1. And the reason we do that is if I make u equal to 4x minus 1 instead of cosine of 4x minus 1, now it says cosine of u, which is something I know how to deal with. I no longer have a composite function. The problem is if I go to rewrite this right now, it would say the integral of cosine u dx. And my variable of integration is x, but the problem has a u in it. So we want to change this dx to a du. And the way we do that, we take the derivative of u. So this is going to say du dx is equal to 4. And then we multiply this dx over to the other side. So this step's always going to look like this, where it says du is equal to 4 times dx. And again, the reason for that is I took the derivative with respect to x, so du dx is equal to 4, and then we multiply the dx over. So if I want to change this dx to a du, I need to have 4 times dx, which would then change into du, because they're equivalent to each other. I don't have 4 times dx, I just have dx. I can multiply it by 4. As long as I also multiply by 1/4. Notice now the problem's the same. 4 times 1/4 is 1. And again, the reason I did that was because I needed 4 dx. So now when I go to rewrite my integral, I have the integral of cosine u 4 times dx, this part right here, 4 times dx, that is equal to du. So I'm going to rewrite that part that I circled as du, and then I have times 1/4. Well, remember, if I have a constant, I can take that constant, I can just move it out front. I can't move a variable out front, but I can move a number out front, 1/4. And now this is something I know how to integrate. The integral of cosine u is sine u plus c. And that can't be my answer because there were no u's in the problem. We should write our answer in terms of x. 1/4 sine of 4x minus 1 plus c. And if that seems super complicated to you, that's okay. After we do a few of these, you'll get the hang of it. Let's try another one. Example 2 says the integral of x squared times the quantity x cubed minus 1 to the 4th dx. The integral of x squared times x cubed minus 1 to the 4th dx. We are going to make u equal to x cubed minus 1. That way I just have u to the 4th, and our hope is that this x squared will become part of my du. So u equals x cubed minus 1. Du then would be equal to the derivative of this, which is 3x squared times dx. So now I'm going to change everything to u's. So this part right here, that's just u to the 4th. to make a du, I need 3x squared dx. I've got x squared dx, so I can multiply by 3 to make my du. There's my du right there, the part that's underlined twice. But if I just multiply by 3, I change my problem. I also need to multiply by 1/3 to cancel out that 3 I just multiplied by. So this part right here, again, that's u to the 4th. 3x squared dx is equal to du. And I've got this 1/3 out front. Now I have changed everything to u's, and it is now in a form that I can integrate. The integral of u to the 4th is 1/5 u to the 5th plus c. We're just going to bring our 1/3 down. 1/3 times 1/5 is 1/15th. U to the 5th. U is x cubed minus 1 plus c. Example 3. Let's go with the integral of x to the 4th times the square root of 3x to the 5th plus 6 dx. The integral of x to the 4th times the square root of 3x to the 5th plus 6 dx. Think about what you believe you should make u equal to. U should be equal to 3x to the 5th plus 6. So that our du is equal to 15x to the 4th dx. I've got square root of u. 15x to the 4th dx is equal to du. When I filled in that 15, I also need to multiply by 1/15th to cancel out the times 15. We can integrate that if we change square root to the 1/2 power. We integrate by adding 1 to the exponent and dividing by that exponent. So dividing by 3/2 is the same thing as multiplying by 2/3. So you have 2/45 times u to the 3/2 plus c. And u is equal to 3x to the 5th plus 6. I don't like that one. This one looks super complicated. Integral of tangent to the 4th x secant squared x dx. And sometimes we just kind of have to guess at what u is going to be and see what happens. So we really only have a couple options here. Remember, tangent to the 4th x is the same thing as tangent x to the 4th, which now looks a lot more like what we've done on the previous ones. Or secant squared x, it's the same thing as secant x, all squared. So try something. We've got tangent x and secant x. If we make u equal to tangent x, the derivative of tangent x is secant squared x dx. That's one that you were supposed to memorize. Hopefully you did. If not, on page 144, I think, might be 244, is a list of all the derivative and integral rules. So du is equal to secant squared x dx. We have du right there. We don't even need to multiply by something like we've done on other ones. We've got tangent x to the fourth, which is the same thing as u to the fourth. We can integrate and replace u with tangent x. One-fifth tangent to the fifth x plus c. Example 5. Example 5, we're given the integral of sine 2x cosine 2x dx. The integral of sine 2x cosine 2x dx. Again, sometimes like the first couple, most of them look like examples 1, 2, and 3, where it's fairly, once you have the hang of it, it's not too bad on figuring out what u should be equal to. Sometimes you just have to try something, see what happens. So on this one, let's try u equals sine 2x. That's one of the things I have here. If u is equal to sine 2x du, the derivative of sine of something is cosine of that thing. Chain rule times the derivative of 2x. And then times dx. And then you want to see, can I make this du based on what I have? Well, I've got cosine 2x dx right there. So I just need to multiply times 2. There's my du. Multiply by 1/2 as well. So 2 cosine 2x dx. Everything I have underlined is du. I've got 1/2, and this is just u. Integral of u to the first is 1/2 u to the second. Just bring down this 1/2. So I get 1/4 u squared. U is sine of 2x. And we are there. Notice if you had tried this differently, if you had made u equal to cosine 2x, this would work as well. We would get derivative of cosine is negative sine, so it would look like this. So I'd have to multiply by -2, -1/2. I'd wind up with -1/2 integral of u to the first du. I'd get -1/4 cosine squared of 2x plus c. Those are equivalent answers. Either one would work. So sometimes you just have to pick something for u, see if it works. Sometimes both would work. Sometimes one might work and the other one might not. Last one, example 6. The integral of that mess. 1 plus 1 over t all to the third times 1 over t squared dt. Because this is to the third, odds are good that that's going to be our u. So let's try that. Let's go with u is equal to 1 plus 1 over t. That's the same thing as 1 plus t to the negative first. So we can take the derivative, move the -1 out front, drop the power by 1. -1 minus 1 is -2 dt. And notice the 1 over t squared is t to the negative second. So there's the t to the negative second right here, dt. I need -1. So here is my du. -1 t to the -2 dt. So I have the opposite of the integral of u to the 3rd du. And we can integrate and go from there. -1/4 u to the 4th plus c, and u is equal to 1 plus 1 over t. That's it for today's notes. We'll be back at it next time.